Hey guys, welcome. Today we're going to solve Leetcode problem number 127 called word ladder. And as always, this is my first time solving this problem with you guys live, so please be patient with me. Okay, so let's get started. And as usual, the way that I solve problems is typically I read the problem statement, and in the comment section above the code, I try to break the problem up into components. Essentially, I try to come up with questions that can help me understand the problem better and also answer any sort of flush out any ideas in my mind. So, for anybody who interviews with uh, you know large companies like Facebook, Google, and whatnot, what I would recommend practicing is practicing explaining thought processes. And essentially, this is what I'm doing right now. So I'm just practicing interviewing essentially. Okay, so let's read the problem statement. Okay, so given two words, begin word and end word, and a dictionary's word list, find the length of shortest transformation sequence from begin word to end word such that only one letter can be changed at a time, and secondly, each transformed word must exist in the word list. Note that begin word is not a transformed word. And there's also a side note, return 0 if there is no transformation sequence. All words have the same length. All words contain only lowercase alphabetic characters. You may assume no duplicates in the word list. You may assume begin word and end word are non-empty and not the same. Okay? So here's a little example here. Begin word is hit, end word is cog, and we have a word list here. The dictionary word dictionary list. So we have hot, dot, dog, lot, log, cog, and output is 5. Let's see, and the reason for that is, so there's an explanation here, as one shortest transformation is hit to hot, so we're changing from letter I to O, and then from letter, let's see what's going on, H to D, and then T to G, and then D to C. So in each transformation, one character is changed, right? Okay. So the goal here is to find the length of shortest transformation sequence from begin word to end word. Okay. So all words must have the same length. Okay. All words contain only lower alphabetic characters. You may assume no duplicates in word list. Okay. Here's another example. Let's see. What else can we assume here? You may assume that begin word and end word are non-empty and are not the same. Okay. Can we assume? Okay, right. So there may or may not be solutions. So return 0 if there is no such transformation sequence. Okay, so we'll have to think about that. So here's another example. Right. The end word cog is not in word list, therefore no possible transformation. Okay, so let's begin asking some questions. So the reason why I like to put put in ask a lot of questions and put them in the comment section is because it's a good way to essentially document the thought process and when you are talking live, sometimes your mind goes blank, right? So the benefit of writing things down into the comment section is for you to essentially refer back to what you had thought of previously, so that you don't freak out and forget things and jumping all over the place. Okay, so let's ask some basic questions. So what are the inputs, right? Output and what is the brute force solution? Identify bottlenecks, and optimal solution, as well as asking. We also have to ask what the other thing that if we can, is to ask what is best conceivable runtime, right? What is the best possible runtime? Okay. And we also should be asking any clarifying question. Okay. And assumptions, right? Okay, so let's start with our first question. So input, we are given string called begin word, right? Another string called end word. Okay, so it's pretty straightforward. We're given two strings, and output, we are outputting integer that is defined to be let's see, what is that called? Length of shortest transformation, right? In this case, let's see. So let's ask some questions here. So what does that mean, right? So the first question that we should ask is, do all words within the list have to be within our sequence of transformation? Do all words within the list have to be in our sequence of transformation? Okay, so that's the first question that we should ask. I mean, essentially what I'm saying is that, what if there are two words? Let's say for this example, there are words such as, let's for an example's sake. So let's say we have the word, let's see, dog and cog, right? Let's say within this example list, let's say we have so many words, right? And then within this supposedly example list, there are two words, dog and cog. Can we say that the shortest sequence is only the two words? Because getting from, let's see, how does this work? Okay, okay, I might be confusing myself here. So let's leave that question there for now, right? Okay. So from what I was trying to say earlier, what I just realized is that we have to identify a starting point, right? How do we identify starting points? And intuitively here is the starting point is the next possible word, is the next word essentially that can be transformed with one character. Let me say that again. So the next word that, when transforming one character of the begin word, will become that word, right? So essentially the next word. So how do we identify a starting point? Okay, any other questions? The other question here is, how do we know that no solutions exist? right? Any other questions? And let's write down the assumptions that we have here. So the first one is right, all words have the same length, right? Secondly, we also know that only lower cases, right? I like to retype the problem statement so that my mind can process the information a little better. And what else? Only lowercase alphabetic characters, right? Meanings there won't be any numbers, right? No numbers, no symbols. Okay, what else? No duplicates in the list. Okay, so there won't be any duplicates. So we might be able to take advantage of that. What else? Begin word and end word are not empty. And the other one is solution is not guaranteed, right? Can be no solution, right? So let's try to answer so any other questions that we should be thinking about? Okay, so let's see, anything else here? So let's try to answer our clarifying questions. So the first one we are asking, do all words within the list have to be in our sequence of transformation? No. Let's see. No. Right? As long as we can find transformations that, as long as we can string together words that connects to the end word, right? As long as we are able to find sequence of words that satisfies our requirements, and in this case is the shortest transformation, right? From each word to the next word to the next word, only one transformation happens, right? Wait a minute. Oh, right. Another assumption here that we didn't write down is only one letter can be changed at a time, right? So that's very important. And the other one is each transform word must exist in the word list. Oh, and another very important thing here is that begin word is not a transform word, right? Meaning that we cannot include our begin word as a solution. Meaning that let's say we have hit and cog. Okay, let's say begin word is one transformation away from end word. That cannot be a solution because begin word is not a transform word, right? If I understand that correctly, meaning that we cannot simply have begin word and end word as our solution. Okay, if that makes sense. So we might have to come back to that. Okay. Okay, let's rephrase this. So the answer to the first question is no, as long as we can let's say find sequence of words that satisfies the requirements, right? And the requirement in this case is that sequence of words that the shortest transformation sequence, essentially. And the second question that we asked is how do we identify starting points? And I think this will be the core of our algorithm here. This may be potentially our bottleneck, right? We have to somehow identify the next starting points, right? So let's list a number of approaches here, right? So let's dig into this. Okay, actually, you know what? Before doing that, let's try to answer this question here. How do we know that no solutions exist? Simply, we just say, you know, no starting word within the dictionary list, right? That, you know, so if there are no, okay, let me say that again. No next word within the dictionary list, right? So if there are no next word, then there's no solution. I mean, but it's a little more complicated than that. How do we know that we are on the right path in the first place? So an approach that's sort of coming to mind, or something that I am sort of thinking about, is this problem is very similar to if you were to it could possibly can be thought of some sort of a graph type problem. Essentially, you know, what we are doing here is that, you know, we have a starting node. Let's say we have the word hit, and we are given a word list of length n, and, you know, we have n possible paths, right? So let's say we're starting from hit. We can we is from here we can pretty much start from the next word can pretty much be anything, right? And we don't really know which path will lead us to the shortest path. It's almost as if we are doing some sort of possibly breadth first search, or some sort of path finding, some sort of shortest path finding algorithm, right? Yeah, so another question that just came to mind just now is how do we know which character to modify, right? So let's look at this here. So we have the word hit, right? So let's say if we want to go from hit to the word dot, right? Oh, okay, it's very obvious here. Hit cannot go to dot, mainly because, why is that? Let me think about this. Given two words, begin find the shortest transformation sequence from begin word. Okay, so just to go back to the objective of this problem, is we're trying to transform a word from the beginning word to end word, and essentially we're trying to find a sequence of transformations by changing that that essentially represents our path from the word hit to the word cog by changing one character at a time, right? So from the word hit to the word cog, you know, if we were to imagine changing one character at a time, what can we do to change the word hit to the word cog? And we have to find a sequence of changes, meaning changes of one character at a time, that will get us to the end word, right? and the word list represents a list of words, a list of possible transformations that can that we can pick from that will result in the N word. Okay, so to answer this question, how do we know which character to modify? We'll know. So just by looking at it, the word hit, really the next possible word here is hot, only because by changing one character, the word hit can become the word hot, right? Hit cannot become dot because it requires two changes, right? The H and the I has to be converted. So H has to be converted to D, I has to be converted to O, and so on, right? So the next possible word is hot, right? Or lot, right? Or even, let's see, what else? So either hot or, okay, only hot, right? So to answer this question is a character that will result, a character change that will result in a match, right? So let's put an emphasis on the word a, right? Only one. So when a character change happens, it will result in a match, right? Okay, so that answers our question. So now let's go back to our algorithm here. So what is the best approach here, right? Maybe a breadth first search is some sort of graph, shortest path finding algorithm. Okay. So let's do this. Let's try to solve this very simple example, right? So it's getting a little messy here. So let's do an example. So we have the word hit, begin word, and for the N word we have the word cog, right? So now, so if we were to imagine the word hit as our beginning node, right? The next thing that we can do now is find out what is the next possible word that we can pick from. What is the next word? So as you can imagine, the brute force way would be to scan from left to right. You know, we'll check here. Let's say the next one is hot. The next possible one is hot, or the next possible one is lot, right? So that would be our next starting point, right? So let's write it out. So the next starting point would be hot. And let's see, right, and going back to right, so the next one would be hot, and the next one would be lot, right? So this would be our second level here. So if we were to imagine some sort of a tree like structure or a graph, so let's call it a graph. So let's say we start from hit, right? Okay, so now from here we see that from the word hot we can either do, let's see, how do I draw this? You know, it's very hard sometimes to trying to draw a graph by typing on this editor here. You know, writing out graphs on a text editor is very difficult sometimes. So let's see, actually the way I like to do it is, let's see here, how can I do it better? So right, so from the word hit we can go to the word hot, or we can go to the word lot, right? So this is starting to become sort of like a tree or like a graph, some sort of graph. directed graph, right, from top to bottom essentially. And from hot, right, so now we are down a level. So let's imagine so that this is a recursive function. So now from hot, what can we do here, right? We can either go to dot here, right, or we can go to, let's see here, so from hot we can go to dot, or we can go to, let's see, hot lot. Oh, okay, so here is where we see duplicate here, right? So hot can also go to lot. Okay, so that is a problem here. Is that a problem? Let's think about this. So hot can go to lot. But why would we do that, right? In order to optimize this, what we could do is at each level, we should be removing, okay, so the question now becomes, should we remove words from its list, from the word list as they are being chosen? Not so sure about that. Okay, let's forget about that from now. Yeah. Okay, let's not do that for now. So okay, let's get back to this. I'm just babbling now. So from now, okay, so here dot, right? So now hot can go to dot, or hot can go to lot, right? So from here so now from dot, right? What's the next possible words that dot can reach? And in this case, dot can reach the word dog, right? So we can go to dog. Let's see, what else can it go to? So dot can go to dog, or dot can go to anything else? Nope, I don't see anything else. Can it go to lot? Nope. Oh, it can go to lot. Okay, it's getting a little tricky here. So this so it can either go to dog, or it can go to lot, right here, right? Okay, so let's look at this recursive call. So we're starting from hit, we go to hot, we go to dot, and then we go to dog, right? From dog, then finally we can get to cog. Okay, which is our final destination here. Another thing that we have to put in our assumptions is n-word exists within the list, right? So whenever our final destination or the next word becomes n-word, then we are done essentially. So we have to do that check every time as we recursively go through this recursion. Okay, so now let's explore the alternative path here. So another question that we should be asking is, what do we return? So in this case, we have reached our final destination, so we'll return the essentially this length of this recursive call, which is 1, 2, 3, 4, right? Let's say hot to dot to dog to cog, or 5. 1, 2, 3, 4, 5. 5 transformations. Okay, so what about coming from lot? Okay, so now from lot we can either go to, let's say, hit hot dot lot, let's say hit hot dot lot. From lot we can go to log, and from log we can go to cog. Okay, and we'll return the length of this and compare the solution, and at each recursive call we'll be returning the shortest between the two paths. And let's also return -1 or 0. We could return 0 if no path exists, or let's return some huge number, right? So that our main function is really straightforward. So okay, so here, so we have a brute force solution, and that is to so let's write down our approach here. Our approach here is to recursively explore all possible paths, right? Starting from beginning word. And so now the question becomes, okay, so we should also specify return minimum path, right? Minimum count, right? Okay, so now the question becomes, let's see, what do we have to do now? You know, something that I just realized is, okay, so now the question becomes, what is the runtime? And I think I know what the runtime is. It's going to be around O of n factorial. So let's, because we are essentially finding all possible, so this would be the worst case, right? Let's say we have a list of words that are connected by one character, right? And for whatever reason the n word doesn't exist within the list, so the algorithm, what the algorithm will do is it'll go to permutation of sequences of the words, right? So this would be the absolute worst case runtime. And space, let's say space would be the length, because we are using stack space. Space would be n, because that's the longest possible sequence, essentially. If you were to imagine we are recursively calling from the begin to the end, and let's say the sequence is the longest possible path, right? And the longest possible path is constrained by the number of words within the list itself. So they would be our space, right? So let's try to justify why this is the case for runtime. So let's say we have a bunch of words like hot, lot, cot, jot, right? And for whatever reason the word cog is not in here, and so what the algorithm will do is that it'll try to go through all possible permutation of these words, right? So we'll start with hit to hot, hot to lot, hot to cot, hot to jot, or hot to cot first. Let's see, hot to lot, hot to cot, hot to jot, and then from there it'll also do cot. You know what I mean, right? So let me try to write it down here. Okay, what I should simplify this. So let's imagine we have the word that are represented by variable a. So let's say those words are represented by these ABC variables, right? And each word can go to the next word with one transformation. And the reason why I think this is in factorial is because if we were to do it in a brute force way, is A can either go to B and C, or A can go to C and then back to B again, or A can go to C and then B, right? And so on, right? And then the next one will start with B, right? So B can go to A or C, B can go to C and A, and we'll do same for C, A to B, C to B to A, right? Because, right. Okay, so now the question becomes, how can we optimize it, right? Identify bottlenecks, right? So what we could do is, we'll return 0. So we can do a little optimization here and there. For example, return 0 if n word is not within list, right? Return 0 if n word is not within list. What else can we do here? Return, let's see, we can also do micro optimization such as not branching out. Okay, so now the question becomes, okay, here let me write something down here. Actually, this should go under optimization, right? Optimization of brute force approach, right? So what can we do to optimize this? So like I was saying before, return 0 if n word is not within the list. So now the question becomes, what about not branching out? Is there a way for us to know beforehand that let's say we gone through this whole path here, is there a way for us to know that this is already optimal, right? Is there a way for us to not having to go through the other branch? Not so sure about that, right? So let's ask some questions here. Can we pre-compute something? Pre-compute. Okay, so some idea just came to mind is maybe we can pre-compute some values, right? That represents distance of something, right? Meaning that, let's see here, meaning that let's say we have the word hit. What we could do is we can compute a distance from the word hit to the word cog, right? Maybe assign some weights to each word. So this will really become like a graph problem here. And why do I think this might be useful is, so let's say for whatever, so let's say we have some sort of weights here, right? Let me think about this. Okay, can we pre-compute some values that represents weights? The reason why I'm not going into coding is because I don't think this is optimal enough to be submitted. So let's try to think about how do we optimize this brute force approach. And if I don't come up with anything within, let's say, 5 minutes, let's just try to do the brute force solution, and we'll just submit that for now. But okay, let's think about this. So let's spend for the next 5 minutes. Let's think about how can we optimize this solution. So now I'm thinking about this idea of possibly pre-compute some values that represents weights, so that let's say the word dog has the lowest weight, for some yeah, let's see here, let's say the word dog. So let's say the weight is the number of transformation needed to transform to the word cog, right? So we know right away that if we were to go from dot to dog, there's only one. The weight of this will be lower than the weight of lot, right? So we don't really have to go to this route, right? Because okay, so this idea may work. Okay, so let's think about this. So what we could do is here pre-compute so let's explore that idea a little bit. So the reason why we are trying to do this weight system is so that somehow we have some values that tells us to whether to go through a path or not, right? If we had gone to the shortest path already with the lowest weights, then we don't really have to go to the path with the high weight. If we know that this current shortest path with the current lowest weight, which is the destination, then we know that that is already the optimal solution at the current recursion. Okay, that's a mouthful. So let's see what that entails here. So so what we could try to do here is pre-compute distance. I can think of it as weight, distance of each word to final word, right? And really what that is the number of character difference, right? Number of character difference. So for example, let's say here, so let's do an example. Let's see if this idea even makes sense. So let's say we have this list, right? So let's do a test here. So let's say we do something like this, right? And let's assign some values here. So let's say from the word hot to cog, the values here is it takes around 2 transformations. So the 2 dot to cog is 2. Okay. Dog to cog is 1. Lot to cog is 2 as well. Log to cog is 1, right? So how are these values useful? So let's revisit this example here, right? So let's copy this example down. So let's say we are starting with the word hit, right? Ideally, what we want to do is we want to go to the route with the lowest weight, current lowest weight. So from the word hit, we can go to hot, we can go to the word lot, and both have the same weights. So for this case, we're gonna have to go through the two So from this point on, we have to explore both paths, right? Okay, so now let's say we start with our next path, the one recursion down, which is the word hot. So now we have to decide between the word dot or the word lot, right? And in this case, we ideally, okay, so from hot we can go to dot or lot, right? Let's see here, dot to lot. Essentially what we have to do here is so they have the same weights as well, right? So 2 and 2, so we still have to explore both of them. Okay, so now from dot, right, we can either go to lot, okay, and because we have this weight, we know that lot has a higher value and dog has the lower value, right? So if we go to dog, which is 1, and then finally we get to cog, so that's it. So as we recursively go through each route, we have to keep track of the weights, the total weights. So starting from hit by itself is 3, right? So 3 plus 2 here, which is 5, plus 2, 7, 1, 8. Okay, so 8. So we know. So now we know not to go to the other path, because let's see. Okay. Let's see. So the reason why we don't want to go to this one is because we have a solution here, and also, so this path is valid, and also the weight of this is lower than this, right? So we don't go to that path. Okay, so now let's say we are back to this recursive call, and this is where it was inconclusive for us, right? Because hot to dot or hot to lot, dot and lot have the same weight. So now the question becomes, so now naturally the algorithm would go to this, right? Because it was inconclusive for us here, because dot and lot have the same weight. So when we are back to this recursive call, we now have to still go through it, right? So lot, so now lot can either go to log, or it can go to, what else can it go to? Lot, go to log, or it can go to dot, right? So now what we can do is, because we already have a solution from this, a valid solution from this path, what we can do before even exploring the paths is we can compare the future sum, and to see if future sum will still be less than current optimal solution. So let's say we have here is 3, 2, let's say 3, 2, 5, 7. 7 plus 2 is 6, right? Let's see here. So we know that we don't need to go to this route because we already have an optimal solution, the sum of all this. So these two paths are identical. We could have gone to hot.dogcog or hot lot log cog, right? So those are the two paths, but we don't have to go through them because we know beforehand that the sum of the future paths will be the same as the optimal path. Okay. Another optimization that we can make is we can create hash lookup. Can create a lookup table. Lookup table word to next to possible next. Right. We could also do that to allow the lookup to be a little quicker. However, the downside of that is we'll be using quite a bit of memory. Yeah, so that may not be a good idea. However, if we do a scan, so that's another bottleneck that we have to overcome, right? So the bottleneck is lookup for next word. So let's answer our questions here. Lookup for next word, and yeah, that's really the main thing here. How do we quickly look up for the next word? Is there like a way that we can do it with O of n one space maybe? O of one space or O of n space? Can we do it in that way? Yeah. You know what we could do as well is we can potentially generate a graph. We could just do that, and the graph will be, so another approach would be, we'll just do a different approach entirely here, is new approach. So let's put it under our new approach here is create a graph with edges, right? So in this case, if we were to do it this way, then let's see, and with this approach we can just do a simple path finding algorithm. Create a graph with the edges. Each node contains weights. Okay, let's not do it this way. Yeah, let's not do that. And it's quite a bit of boilerplate code that we have to write. Too much code. Okay, so let's, for now, what we'll do is we'll optimize our brute force approach by pre-compute see. So what we'll do for now is we'll essentially to sort of optimize our brute force approach is we'll compute distance, weights from a word, from each word to the n word, and we'll be using these weights to sort of tell us to whether branch out or not. Okay, and let's see. Yeah. anything else we can do? Yeah. Okay. So the worst case of this algorithm would be O of n factorial. Best case, if we were to find an optimal path quickly on the first few recursions, then the best case could be linear. This is, yeah, it's a little messy to find out. So yeah, let's try to implement this algorithm here. So let's start with our brute force approach, and then we'll optimize from there, right? Okay, so as I was saying earlier, our brute force approach is to recursively go through each path, right? So let's define some helper functions here. So the first helper functions that we need to have is find, get. So let's make this private. So since we are implementing this in a class, and it's going to be a private helper, so we'll call it get list next, right? Get a list of next words, right? And we'll pass in current word and next word, right? And let's see, what else? What am I doing? And list of words, right? So we need to do that here. So we'll do that. And the other helper function that we need to define is called get score, right? And really what that's doing is that it'll give us the number of difference, like how much distance. It'll give us a weight or distance value from source word to dest word, right, to destination word. So let's pass for now. Okay, so and let's define our recursion. Okay, yeah, let's do that a little bit later. Okay, so let's do it. Let's call it recurse. So, and will be passed in a list of word and cur and dest word. Cur word, dest word. Yeah, and that should be it. Okay, and as I was saying earlier, will also have a lookup score, right? We'll have a score. Let's call it score. Score lookup. Let's call it score lookup. And we need to be, because this is a class, what we can also do here is we can keep track of current optimal solution, current optimal score. So let's call it self min score, right? Min score. So this will be our global variable that we'll use. So min score. So let's set this to max. So let's import this. So what we can do here is, so let's look that up just to be sure. Python max size. Right, sys.max size, right, just to be sure. So let's initialize that to sys.max size, and we'll be also keeping track of min distance, which is the same here. Okay, So now we have those global variables. Okay, that's good. Okay, so let's pass for now. Okay, so now let's get into the meat of our algorithm here. So we are given, let's see what's going on here. Okay, so we are given begin word, end word, and word list. Okay, before we do anything, we should go back to our assumptions to see if we missed anything. Okay, right. So the first thing that we have to do right away is check if end word in list, right? So this is our special case. And we can, in Python, we can just do something like this, which will take a linear time. So if it's not in word list, return 0. Okay. Okay. So the next thing that we do now, the next thing that we have to do now is we have to pre-compute our score lookup. So we can simply do something like this: initialize a hash map, and for each word in word list, we'll compute the score, right? Score lookup word equals to self dot get score, and it's going to be a score. The score is going to be a distance of the the current word to the end word. Okay, so that's that, simple as that. So let's quickly implement our get score. Okay, so how can we do this quickly here? Because each word, because we can assume that the words we have the same length, we can just do a simple comparison. So I in range of length src and count equals to 0 if we just do a simple comparison here. If the word of this, if the source word is, if the source character is not equals to this character, then we'll increment count, and then in the end we'll return count, right? Simple as that. Okay, so now the next thing that we have to do here is call our recursion function, and let's see, and really all we have to do here is we pass in the beginning word, we pass in end word. So let's just keep the naming consistent here. End word, a list of word. So yeah, let's keep the naming consistent again. So word list, let's see, word list, and score lookup, and then finally we'll be returning. Okay, so the first thing before returning the results is we will be getting it from here, right? So we have to check to see if self.min dist, if for whatever reason it equals to sys max size, this just means that no solution exists, so we just return 0, else we'll return min dist. Okay, okay, that's that. Okay, so now, so let's comment a little bit. Score recurse to find solution. Okay, so now let's go to the meat of the algorithm here. Okay, so right, so we have a current word, n word, word list, score lookup, right? So there are a number of decisions that we have to make here, right? The first decision that we have to make is whether, okay, so the first thing that we have to do is get a list of next words, right? Decide whether to recurse to the next word, and we do that by comparing current score, future score to the current min score, right? So we also have to do that, right? Score. So let's do that. Okay. So another thing that we have to do is we have to check to see if for whatever reason cur word equals to n word, then we store our results, right? So we store results here, update global results, and we should be also keeping track of a current distance of the path. So that will be 1 initially, including the word itself. So let's call this word count. Okay. Okay, initially the score should be let's see. It should be the begin word. Okay, you know what? Let's make score 0 initially. Right. Okay, so now what we have to do here is we have to check. Okay, so another thing that we have to do here is, let's see, what am I doing? Okay, so the terminating condition is when current word equals to n word, right? So another thing that we have to think about is what happens if there are no next words, right? We'll just return. Okay, then there would be no solution essentially. So get a list of next words, and then finally after we get a list of next words, for each word decide whether to recurse to the next word, right? And where we decide is by comparing our current score to the current global min score, and yeah, okay, and that should be theoretically that should be it. Okay, so let's do that. Next words, can just call our helper function here. Let's see. Okay, so we do that here, cur word, and we'll also be passing in word list. Okay. Okay. Another thing that we have to do here is we also have to be keeping track of current words. Okay. we also have to, so that we don't get into infinite loops, that the other thing that we have to do is we have to keep track of current how do we call it, we have to keep track of words that we have already chosen, right? So let's call it chosen already. So okay, you know what, since we are okay, so this would be a set, so we'll be using a set here. Right, so we'll pass this set into this. Okay, I don't like the way that this looks. It's quite crowded. So let's quickly move our square lookup into our. So let's make that our global variable within our class. Square lookup. So let's set that to none for now. So let's get rid of that. We do the same for chosen, which is a set. Initialize that to a set. And okay, that should be good for now. Okay, yeah, square lookup makes sense to be global. Yeah, let's leave chosen here. Okay. Yeah, so let's initialize this to an empty set, and what's going to happen here is we'll be populating it here. Let's see, what else are we doing? Okay, so we have, so passing into our recurse solution, we're passing in the beginning word, the end word, word list, initial score, which is 0, word count, which is initialized to 1, and chosen, which is a set of words that we have already chosen as we recurse to our sequence. As we recurse, how do we say it? As we recurse to the solution, to the paths. Okay, that's a better way of saying it. Okay, so now, so the first thing that we're doing here is getting a list of next words, right? And we're calling our helper function here. We're passing in the current word, word list, and chosen. Okay. Okay, so now, so now what we're doing is we're traversing to each word within the list, and what we are doing here is, let's see, what are we doing? Is that, so for each word, as long as the word, so the first thing that we have to check is the word. If the word is not equals to current word, and word is not in chosen, right? Meaning that it's not within a list of words that we have already seen currently within our current path, right? And so here what we're doing is so if the word is not the same as the current word and not in chosen, and we have to get the score of this word, get score, right? And if the score of this word is word to cur equals to 1, then we store this word into our list, right? So we append it, and finally we return next list. So essentially what I'm doing here is that I'm checking to see if the word, if it's not the same as the current word, not in chosen, and the score from the word to destination, which is current word, is 1, then we append the word to the next word list. Okay, so now that we have a list of next possible words, the next thing that we now have to do is deciding whether we want to recurse down the path or not. And the way we do that is by check if future score is less than current min score, right? So that's the first check that we have to do. So we can do a lookup. So let's say, so we do a lookup here. So we have a score lookup. Next word. So if current score plus s is less than self dot min score, if it's still less than current min score, then we recurse one more level down, right? And now we are passing in this next word, leaving the same n word as the same variable, and we update our score to be score plus s, and we are also incrementing our word count by 1. Chosen, we also have to add our word to chosen set, next word. And once we're done with this recursion, we also have to remove that word from the set. So just to verify, let's see if I'm removing the word correctly from the set. Removing from set Python. So just to verify. Okay, so that's right. So we call remove. So chosen, we add the word, we recurse with the word, we remove, and that's all, right? And really this should be it. So now let's update our block of code that updates the global solution. So if for whatever reason we get to cur word, if for whatever reason cur word equals to n word, then we know that we have reached our destination. So now really all we have to do here is we calling min in Python is just returning, it's just a function where you pass in values of integers, and it'll return the value that is the minimum. And in this case, we're comparing between current score and the current global minimum score, right? And we do the same here for distance. So min dist, we call it min dist here, and we'll do the same here. You know what? Yeah, just to keep the naming consistent. So let's call this dist. Yep. Okay, and that should be it for our solution. So let's just do a quick run. I don't expect it to work the first time, but let's see what kind of error we're getting. Okay, so right away we are getting, what is the error? Runtime error 106. Let's see here. Okay, what did we call here? Min dist. Yeah, dst, let's call it. Yep, the naming was not right. Okay, so let's see what this gives us. Okay, nice. So we are getting what we expected, which is that. Okay, so let's see if it works. If this also works with the other one here. Just a very simple one. Let's see, test case. Okay, let's see. Can we do it like this? Run code. Okay, so nice. So it's detecting that the word cog is not within the list. Okay, so now let's do, what else can we do here? So let's just to be sure, let's print out. So as we are doing this, yeah, get rid of that. So as a debug, so let's print out. Let's keep track of current words that are being considered. So let's just, as a debugging variable, so we do something like this, and then we'll also append keyword. Okay, and then whenever we hit our final destination here, okay, so we'll do something like this, and then at the end of the recursion we'll pop the word. Just do a quick debugging. I just want to see if the words are correctly chosen here. And we'll print out whatever is here. Let's see if this works. Okay, so seems to be doing what I expected to do. So the code went through hot dot dog lot. When it gets to dog, it doesn't know. Let's see. There's no way of knowing from there. Yeah. See, 1 2 3 4 5. Hit hot dot dog log. Okay, this should be optimal enough. We'll see. So let's see if this even works. Can we even submit this code? Okay, so let's try to submit it. And okay, what's going on? The code doesn't even run. What's going on here? Let's see if this works. doesn't work for a simple input. Solution has no attribute min dist. Oh, not okay. Gotta fix the naming here. Okay, let's try that again. Uh-oh, that's not good. Wow, the naming is all over the place. Here, let's see. That should fix it. Okay, let's try again. Yep, the solution is not optimal enough. So let's see how many cases did we solve. Okay, we got through 19 cases. Okay, yeah, so it took me a while, but I was able to come up with a brute force solution. But even with the micro optimization that we made, it's still not optimal enough. But yeah, let's call it a day. And thanks you guys for watching. And I'm going to read the solution now. See you guys next time.